The Group 1 elements, commonly known as the alkali metals, are quite different from most other metals in the periodic table. These include lithium, sodium, potassium, rubidium, cesium, and francium. Unlike what we typically expect from metals, such as high strength, high density, and high melting points, the alkali metals are actually relatively soft, have low densities, and melt at comparatively low temperatures. Despite their softer physical nature, they are significantly more reactive than most other metals. They react vigorously with water, oxygen, and elements from Group 7 such as chlorine, which we will discuss in more detail later. As you move down the group from lithium to francium, the reactivity increases even further. Cesium, for instance, is so reactive that it can spontaneously ignite at room temperature. Along with this increase in reactivity, another trend observed is that both the melting points and boiling points decrease as you go down the group. A good way to remember this reactivity trend is to think about table salt, which contains sodium. It doesn't suddenly burst into flames when you sprinkle it on your food, but cesium just might if it were used instead. A fundamental aspect of chemistry is understanding and explaining such trends and properties. So why are alkali metals so reactive? If you recall from our previous discussion on electron arrangements, all atoms aim to have a completely full outer electron shell to become stable. All alkali metals are part of Group 1, meaning each of them has just one electron in its outermost shell. Therefore, to achieve a stable configuration, all they need to do is lose that one single electron, which is relatively easy since there is only one to lose. When they do, they form a 1+ ion, having lost a single negative charge. Now regarding the trend of increasing reactivity as you go down the group, as we descend through the group, each atom's radius becomes larger, and the outermost electron is situated farther away from the positively charged nucleus. Because the attractive force between the nucleus and that lone outer electron becomes weaker with increased distance, it becomes easier for the atom to lose that electron, making the atom more reactive. Keep in mind, reactivity simply refers to how easily atoms can lose or gain electrons to undergo chemical reactions. Since alkali metals can lose their outer electrons so easily, they almost always form ionic compounds when reacting with nonmetals. In an ionic compound, such as when sodium reacts with chlorine, the metal atom donates its one outer electron to the nonmetal, so that both atoms achieve full outer shells. This transfer of electrons results in oppositely charged ions, a positive sodium ion and a negative chloride ion, which are then held together by strong electrostatic forces known as an ionic bond. This specific reaction produces sodium chloride, which is nothing other than common table salt. In general, regardless of which alkali metal is used, the resulting ionic compounds tend to be white solids that readily dissolve in water to form colorless solutions. Now that we've covered the general characteristics and reactivity of alkali metals, let's look at how they specifically react with water, chlorine, and oxygen. When an alkali metal is placed in water, it reacts vigorously, producing a metal hydroxide and releasing hydrogen gas. For instance, sodium reacts with water to produce sodium hydroxide and hydrogen. As mentioned earlier, the further down the group you go, the more reactive the metals become, and therefore the more energy is released during the reaction. From potassium onwards, the energy released is so high that it ignites the hydrogen gas, which can be seen as visible flames. These metals also react strongly when heated in chlorine gas, forming white metal chloride salts. For example, sodium reacts with chlorine to produce sodium chloride, and again, the intensity of the reaction increases down the group. When alkali metals react with oxygen, they form metal oxides, though the exact type of oxide depends on the specific metal involved. For example, lithium reacts with oxygen to form lithium oxide, written as Li2O. Sodium also forms sodium oxide, Na2O, but can additionally react to form sodium peroxide, Na2O2. Potassium can go even further and react with oxygen to produce either potassium peroxide, K2O2, or potassium superoxide, KO2. That's quite a variety, and you don't necessarily need to memorize the reasons why each compound forms. A more effective strategy might be to simply make flashcards and practice these reactions regularly, especially if you're preparing for exams. And that sums up everything you need to know about alkali metals for now. If this explanation helped clarify things for you, please consider giving us a like and subscribing for more content. We'll see you in the next video.